All right. Hello, everyone, and welcome to our first AAS press conference of the day today. It is 12:15 Mountain Time or 2:15 Eastern Time on January 11th, and our press conference is going to be about SDSS passing the torch to phase 5. My name is Macy Huston. I am the Astrobites media intern for this week, and managing this press conference today, I am joined by Susanna Kohler, the AAS press officer, Carrie Hensley, the AAS Deputy Press Officer, and Haley Wall, the AAS Media Fellow. They will be handling the Q&A and all the technical problems that might arise while we are here today. There will be 3 press releases for each of the presentations going on today. Those will be available on the AAS website, as well as on the AAS Press Twitter account. Additionally, all of the materials from yesterday's press conferences are available in the press kit now. I do also want to recognize that there was initially going to be another press conference today, earlier this morning, about satellite constellations and dark and quiet skies. That one did end up getting canceled, but we're hoping to bring it back together as some sort of standalone event sometime in the future. So just to go over the ground rules of what we'll be doing during the press conference today, we are currently recording and live streaming this event to YouTube. I'm going to give a brief introduction to the topic and introduce our panelists and their presentation titles. Then we will go through each of the panelists in order and then move on to the Q&A session. We are asking attendees to type their questions into the Q&A feature here on Zoom, and be sure to indicate your affiliation and which presenter your question is for. We also want you to know that you can upvote others' questions to raise their priority in the queue if there's something you're particularly interested in hearing about. We have also asked presenters to not answer questions via text during the presentations because we want to be able to answer these questions out loud during the Q&A session so that people who are just joining through YouTube are also able to see the answers. So our subject for this session is the Sloan Digital Sky Survey, passing the torch to phase 5. We will start with a presentation from Rachael Beaton of Princeton University. The subject will be almost 1 million stars and counting, mapping the history of the Milky Way with Apogee and beyond. Following that, Karen Masters of Haverford College will present Galaxies Assemble. MaNGA team releases largest ever collection of 3D maps of nearby galaxies. And then our last presentation for this session will be from Juna Kollmeier of the Canadian Institute for Theoretical Astrophysics, University of Toronto. And that presentation will be about SDSS-V, robots see first light. And now I would like to hand it over to Rachael.
Thank you so much. In addition to talking about Apogee, I'm also going to introduce the Sloan Digital Sky Survey, or SDSS-4, and how we are excited to conclude this phase of the survey and pass the torch on to the next phase. To repeat, my name is Rachael Beaton. I am a research fellow primarily at Princeton, but I'm also affiliated with Carnegie Observatories, and I serve as the Apogee 2 Science Working Group Chair and as the co-chair on the Committee of Inclusiveness and SDSS. So the Sloan Digital Sky Survey has been mapping the universe for and releasing that data for 22 years. We just had our 17th public data release in December 2021. And I wanted to highlight this lovely plot from the data release paper, which is showing how our data grows over time. In particular, that DR17 has 245 terabytes of data. And we also maintain all of our previous reductions, and that amounts to 407 terabytes of data. Now, I know with the new projects that are coming online, like with the Rubin Observatory LSST, this is a small amount of data compared to what they're thinking of, but for the size of our project and the size of the scale and the amount of resources that we have, this is just a tremendous amount that we maintain and keep available for the public. Now, what is that data, that wonderful data? We have imaging. Our imaging surveys cover about 35% of the sky, one of the big first digital sky surveys. And we also have over 5 million spectra of stars and galaxies in different components of Sloan. And it's hard to imagine an astronomer who hasn't intersected with Sloan data in some way or another. Now we're here to celebrate the conclusion of Sloan 4, which ran from 2014 to 2020. And Sloan 4 had three constituent surveys: the Apache Point Observatory Galactic Evolution Experiment, or Apogee 2, the second phase of the Apogee project, the Extended Baryonic Acoustic Oscillation Spectroscopic Survey, or EBOS, and the Mapping Nearby Galaxies at Apache Point, MaNGA survey, which was taking integral field unit observations of galaxies. Now, EBOS actually finished last year and we celebrated their conclusion, and then we got to celebrate again when they released their large science results last year. So today we're here to celebrate the conclusion of Apogee 2 and MaNGA. We will have three presentations. The first one will be about Apogee that I will give. The second will be about MaNGA, which will be given by Karen Masters. And the third will be given by Juna Kollmeier about SDSS-V and how excited we are for the next phase of the project. Okay, so almost 1 million stars and counting, mapping the history of the Milky Way with Apogee and beyond. So what is Apogee? Apogee is a survey of our galaxy. And what's unique about Apogee compared to other surveys is that we work in infrared light. And why do we do that? So this is a map of the Milky Way galaxy in the visual light, the light that we see. And I'm going to overlay some of the structures in our galaxy, like the disk, the central flattened part, and the central bulge. And then the halo is this dark, the rest of it. And you'll note that in that galaxy, you see these dark patches. And that's obscuration by interstellar dust. And that makes it very difficult to study all components of the galaxy in visual light. So Apogee works in infrared light. So here's that map, optical map in the background here. And as beautifully illustrated with our logo, Apogee lets us shine a light on the galaxy in infrared where the extinction isn't so bad. And we can actually look at all components of the galaxy using the same data set and study all components of the galaxy. And we, the goal that we set out to do 15 years ago was to address really big questions, like what are the dynamics of the different components of the Milky Way? What is the chemical enrichment of different components of the Milky Way? Can we actually determine the ages of stars across the Milky Way and begin to piece together its formation history? And we've even looked very granularly at things like, are the planet hosting stars different from the stars without planets? And all these kinds of questions are what we set out to do by getting this big data all across the galaxy. Now, the way we do that is by taking spectra. And this is a plot of the Apogee wavelength range. And it's organized by the familiar temperature sequence of stars, O, B, A, F, G, K, M. So Apogee was originally optimized to work sort of in the G and K regime, where you can see all of these features, which are spectral lines from elements or molecules in the atmospheres of stars, where that part of the spectrum is particularly rich in different features that we can measure, particularly information rich. However, in Apogee 2, we've really expanded to be able to use all different types of stars. Not everyone is perfect, we're still working on that. But we have all of these stars that we provide data for across the galaxy. Another thing that was unique about Apogee 2 is we're no longer working just in the Northern Hemisphere at the Sloan Foundation Telescope. We're also working at the DuPont Telescope at Las Campanas Observatory in Chile. And the really important part about this is, again, we want to view the entire galaxy, all of its different components on the same set of data, the same types of instruments to minimize systematics. And so if we only observe from the north, there's a part of the sky and a very important part of the galaxy that we can't actually observe. So by also working in the Southern Hemisphere, we recover this part of the galaxy, so part of the bulge and a big chunk of the disk, as well as getting access to the small and large Magellanic Clouds. And this is really giving us the full view of the Milky Way. So over about a decade of observation, we've taken data in 2,000 individual fields that were targeted with plates. And here are two examples of a plate from the north and the south. And on this map of the Milky Way, each one of these circles represents a field, and it's coded by the different phase of the survey. And I just think this just vividly illustrates how the different components of the survey fit together to start to map the full galaxy. But you also note all this empty stuff, which hopefully we'll see how we're going to fill that in Sloan 5 in the last talk. So in data release 17, we're releasing data on nearly 1 million targets. There's about 2.6 million spectra. You'll note that that means that we get multiple observations of individual targets. So we actually have multi-epoch motions of those stars. I showed you how we measure stellar types from the spectra, the temperature sequence, but we also measure up to 20 elemental abundances in the spectra. And this plot is actually showing you a very metal-rich star at the top and a relatively metal-poor star at the bottom, which again shows you how visually shows you how we can measure these things from the stars. Now you might think, well, there's many more than 20 elements in the periodic table, but what's important about the 20 elements in Apogee is that we actually cover the 6 most common elements in the human body, which accounts for 97% of the mass of the human body, are all spanned by Apogee across all portions of the galaxy. And this is really important because one of those questions we want to ask, and the reason that we're going after the history of our galaxy, is to understand how these elements were formed over time in the cores of stars and how all of those processes work that eventually allowed us to be here on Earth. And that's what's really important about all of these elements going into Apogee. And then lastly, because this is something that I'm so proud of, in addition to all of this data that we provide about the spectra, we also have a tremendous number of value-added catalogs in data release 17 that have things like distances, binary identifications, galactic positions and orbits, and star cluster membership. And the idea is that you can come to our database, to our website, and you have science-ready data at your fingertips. Come up with a question, you can pose that question and start investigating that question without having to make your own pipelines and your own development. And if you find something that's not quite right with our data or something you want to change, all of the intermediate and raw data is there too with all of the codes, and you can go in there and do it yourself. So this is really aimed at bringing everyone into our data set to study the Milky Way together. Now, to talk about the science that's feasible with this wonderful data is impossible in something so short. So I made this word cloud from the abstracts of the 448 refereed papers with Apogee in the abstract. There's about another 500 non-refereed papers that I decided to exclude for the moment. But it really highlights that Apogee is all about measuring the chemical compositions, the metal compositions of stars and stellar systems, and just a tremendous amount of things that we can do from that. And I'm pretty proud, and I think this is probably a lower limit, of the 61 PhD theses that have used SDSS-3 and SDSS-4 data. But today we're here to celebrate the mapping component of Sloan. It's the thing that has consistent through all the phases of Sloan, through all the constituent sub-surveys. So I want to show you the Apogee project's final map of the Milky Way at the conclusion of a 15-year project. So this is an artist's impression of the Milky Way. It's pretty good, it's pretty accurate. And roughly here's where the sun is in this diagram. And now I'm going to overlay a density map of the targets in Apogee with their actual galactic positions. Oops, sorry. And here it is, where blue is the particularly dense regions where we have lots and lots of targets. And then yellow is the intermediately well targeted. And then the individual red dots are one target. And remembering that all of these targets have the radial velocities, the spectra, the 20 elements, the stellar typing, just an incredible density of information that can be mapped onto this map of the galaxy. And you can answer so many questions, start to pose so many questions and find the answers. But something that's pretty exciting about Apogee 2 and very special about Apogee 2 is we didn't just limit ourselves to the classical Milky Way disk. We actually are reaching out beyond the Milky Way disk into its halo to study its satellite galaxies. And we even have a relatively dense sampling of different fields and star clusters in the Andromeda galaxy, which is quite far away on this visualization, this top-down visualization. And so I'm going to zoom in here really quick to show you the coverage in the galactic halo. And I will let you know that I made the points a little bit bigger here, so just keep that in mind. But here is that map of the galaxy that we were looking at before, and that fits in about right here, roughly. And you'll see all these probes where we went very deep and we looked for a very long time in different areas of the sky to actually look at some of these constituents of the Milky Way that we think in the lambda CDM paradigm are very integral and extremely important in building a Milky Way-like galaxy. That includes extensive mapping of the Magellanic Clouds, the Sagittarius dwarf spheroidal, the Fornax dwarf spheroidal, and then 6 additional dwarf spheroidals. They're here, but it got busy if I labeled them all, and stars along this line of sight to those galaxies. So Apogee has really mapped not just the Milky Way, but we're also extending our mapping to the Magellanic Clouds and the other constituent galaxies of the local group. I'd be remiss if I didn't take a moment in this difficult few years that we've had to highlight all of the wonderful people that have worked on Apogee over its 15 years. I think that's something we've learned in our relative isolation, is how important all of these people are to us. So there's 15 years of teamwork encapsulated in a couple of images. And what's really great is a large fraction of these wonderful humans are going to be working in Sloan 5 Milky Way Mapper, where we're just going to continue to map the Milky Way in a much larger scale. And so that's Apogee's map of the Milky Way and our attempts to map the history of the Milky Way. And we're just really excited to have gotten all of this done and completed in this difficult few years. So thank you.
Okay, hello everyone. My name is Karen Masters. I'm a professor at Haverford College in Philadelphia. And I have been for the past several years the spokesperson for the Sloan 4 project, which I don't need to introduce to you because Rachael did such a fantastic job of introducing it. I get to just tell you about the part of it that is closest to my scientific interests. That is the part where we're mapping nearby galaxies, although more distant than the galaxies Rachael talked about, kind of the next layer out. And we're mapping them in much more detail than has ever been done before, and releasing this final data release 17, releases the largest set of them in existence. So as Rachael introduced, the early surveys in SDSS did a wonderful imaging survey, and every galaxy in the MaNGA sample is selected as a galaxy from that imaging survey. Actually, not this one, this is the Whirlpool galaxy, but it makes a nice illustration point. How MaNGA differs from these imaging surveys, though, is that it's a spectral mapping survey. So after taking these images, SDSS went ahead and took a single spectra for like 1 million of these galaxies, right? But it was 1 spectra per galaxy. And as astronomers, extragalactic astronomers, all astronomers get excited about spectra because of how much information we can get out of those spectra. And so the spectra, we can read it like a barcode, which can tell us about the ages, chemical makeup, motions of stars, where stars are currently forming. We can also learn an enormous amount about the ionized gas in the galaxy, the amount of it, its motions, and pick apart some information about what's ionizing it, whether it's star formation or accretion onto a supermassive black hole or other kinds of exciting things. So it was great that we had single spectra of 1 million galaxies, and tons of papers make use of those data. MaNGA wanted to go a step further, and instead of taking 1 spectra, and particularly for nearby galaxies, that spectra is often right down in the center of the galaxy. Whoops. MaNGA instead takes many spectra across the face of each of the galaxies in the survey. And so this is an example of 127 circles placed over this Whirlpool galaxy to illustrate how that works. This was done by developing some new instrumentation to go onto the SDSS telescope at Apache Point Observatory. We developed these bundles, fiber bundles, where we take optical fibers and bundle them into a hexagonal shape into these little pieces of equipment called ferrules. And in this illustration, you can see how the spectra of this Markarian galaxy differs from the central point to the outer point, and we can learn a lot about the physics and the astrophysics of what's going on in that galaxy. So this turns out to be an enormous amount of data per galaxy. We put together something called a data cube for each galaxy. So these observations can be made and turned into images, but the images can be at any wavelength across the range of the spectra, or you can pick out a spectrum at any point in the image, at any spatial pixel. So we release those data cubes. We also generate maps of properties that are derived from the data cubes. So these are maps of things like where the ionized hydrogen is in the galaxy, or the oxygen, or the silicon, or the nitrogen, or any species we can identify. Through the Doppler shift, we can identify how that gas is rotating. And so I have an illustration of that here. But we can also do separately how the stars are rotating, the random motions of stars, revealing the difference between the bulge in this galaxy and the disk that's rotating. And the bulge is kind of like a swarm of bees, and even more information like the ages of the stars, where stars are forming, all kinds of information. So it's lots and lots of data per galaxy, and MaNGA is lots of galaxies. And SDSS enabled us to do that by using the SDSS plug plates, here illustrated in a beautiful art exhibit that happened in Scotland. You can see one of those plates, and on the right, that's me having a go at plugging some plates, and the black fibers are actually the MaNGA bundles that would go into this plate. So we could do 17 MaNGA bundles at once, which allowed us to have a really nice, fast survey speed across 6 years of observing. We have observed just a little bit more than 10,000 galaxies with MaNGA. So this illustration here, this mosaic, is the Whirlpool Galaxy image made up of just 10% images of just 10% of the MaNGA samples. It's just 1,000 of them. But remember, each one of these also has all of these maps. And so I popped out one galaxy with 9 maps as an illustration. We make over 30 maps per galaxy. So it's an enormous amount of dimensions of data. Just to illustrate that a little more, here's a more technical overview. This is about half of the sample now, showing the throughput through the bundle in total intensity, so the amount of stars. The insets illustrate kind of why we went for such a large sample size. We really wanted to cover parameter space of galaxies. So now in those insets, each galaxy is a single point, and they're plotted in the one case at their color and brightness, and the other one it's mass and rate of star forming. By filling in this parameter space and doing it in this resolved way, we get lots of information about how galaxies change over time. So now I'm going to flash through a few other maps of these same galaxies in the same layout, just to get a sense of the amount of data, but I'm not going to stop very quickly. Again, this is kind of like the total light in stars. Here we have where the ionized hydrogen is in the same galaxies. This is a parameter which measures the age of the stars, and here we have the motions of the stars from the Doppler effect. I keep mentioning stars, and galaxies are made of stars, and in particular the light from galaxies is the sum of the light of all the stars in the galaxy. So to understand the MaNGA data, we really needed to have a really good reference library for how stars work in the same range of wavelengths, in these optical wavelengths. So making use of the MaNGA instrument when Apogee was observing, actually, so when MaNGA couldn't observe galaxies because it was too bright, we also ran this MaNGA Stellar Library project, or MaSTAR, and we're releasing the final dataset for MaSTAR in DR17, or we released it already. So on the right here is a Hertzsprung-Russell diagram. So this is luminosity and temperature of stars in the MaSTAR library. This is 12,000 stars observed through the MaNGA instrument. So it's ideally suited to help us improve our analysis of the MaNGA data and really make the most accurate possible models of the ages and properties of the stars that are making the light in those galaxies. I've kind of emphasized how complex the data is. Make it open, we make it available to the public. We also want to try to make it accessible to the public. And so we've also developed this suite of tools called Marvin to help with the access and visualization of MaNGA data. Marvin is available as a web tool. So you can go to the dr17.sdss.org/Marvin, and you can put in any galaxy and explore it in the web and kind of look at the different maps and look at spectra at different points. It is also available as a suite of Python. It's a Python module, so you can install it and use it in a more powerful way through Python. Using the same technique as Rachael, I took a word cloud of the 513 abstracts I found in NASA ADS that include the words both MaNGA and galaxy. And so we're doing a lot of science to do with galaxies, with a lot more to come now that the sample is complete. Really excited to see what comes in the future. And, you know, as SDSS spokesperson, one of my big jobs is to kind of coordinate the writing of the data release paper and make sure that we get this sort of documented and out to the public. So I'm really delighted that data release 17 happened on time in December 2021. And we have the data paper with the 335 co-authors listed there. It's quite a lot to wrangle, but it's a real pleased that it worked well, and it's out there for everyone to read. So here we are. So just to wrap up, we're releasing the largest ever collection of 3D maps of nearby galaxies with MaNGA, as well as a complete stellar library to help with this analysis. All of this data is publicly available and accessible with help to access and visualize it, and we invite you to see what you'll find in the data set. Thanks.
Okay, everybody, can you hear me? Seems so. I'm Juna Kollmeier. I am the director of SDSS-V at the University of Toronto. I'm so thankful that you guys are all here today listening to this incredible celebration and achievement, both of the conclusion of SDSS-4 and also this major milestone for SDSS-V. So first and foremost, I want to thank SDSS-1 to 4. And you just heard these beautiful presentations, which is just the tip of the iceberg. I mean, the tip of the iceberg of what science has been accomplished in these phases, and all of the partners throughout all of the phases. Rick Feinberg, the former AAS press officer, used to call SDSS the Energizer Bunny of sky surveys. It just keeps going and going and going. And I am so proud to say today that we are indeed going and going and going, and this time with upgrades to the Sloan telescope at APO, and now with robots on the sky. So we continue the legacy of our predecessors in trying to understand the structure of the universe. That's what we're about. In this phase, we're focusing on stars and black holes that make up galaxies in order to understand the physics of these objects and to understand it more deeply and probe them temporally, to understand how they evolve on timescales ranging from days to decades. To that aim, SDSS-V has these 3 mapper projects: the Milky Way mapper, the local volume mapper, and the black hole mapper. And the number of targets in each of these things is just ridiculous. It's 10 to the 7 targets. It's huge numbers of stars, black holes, and spectra of with our local volume mapper going into the Milky Way and nearby galaxies in very, very high detail. Now, in order to achieve the goals, the scientific goals of these projects, we need a lot of targets. But we also need to be able to quickly visit and revisit these targets. And this wasn't practical with the plug plates that Karen just showed you a picture of. And they've served SDSS in the community for many years, for 22 years, as Rachael said. And we're so grateful for that. But they weren't up to the task of what we need to do here in this phase of SDSS-V. And that's why we needed to build these robots. Now, we knew when we started this project that this was going to be challenging. We knew we had an aggressive schedule. We knew we had a big hill to climb in many different respects, logistically and technologically. But we knew it was worth it. And one of the things we didn't, of course, foresee was that a global pandemic would affect our entire collaboration. So it's really an understatement to say how excited I am to be able to report to you that our robots are now on sky collecting spectra. And I know that sometimes it's tempting to just do victory dances, and I will tell you I've done a few of those over the past few weeks. But I thought it might be more interesting to describe a bit of our journey to this point, and a journey that was not easy and that is not over. So to that aim, I thought I would use the meme format. So it started with a couple of us in a room in New York City, trying to figure out how we were going to go about this ambitious project, and of course with all of these science goals in mind, and how it's going. On the right, I'm showing the observing and commissioning team and the spectra in the lower right hand there, coming from the telescope. So it's been a long road to this point. Of course, it started out with conferences where we could all talk, and there's our Milky Way mapper program head, Jennifer Johnson, giving a talk at our kickoff meeting in 2018. And this was our MC. And now we're doing a lot of Zoom. And you can see from some of our expressions there in the right-hand side that it's been a tough road. But we're so grateful to have this ability to convene electronically when we couldn't convene in person. How it started with we had these incredible designs for these two focal plane systems. And then just as we were trying to get our machinery built in laboratories, those laboratories closed down. And so the creativity of our team and the resilience of our team, I'm showing there Stephanie Wachters, the lead systems engineer, built a cardboard version of this to work out interface issues that she couldn't get her hands on because they were in Columbus. And I'm happy to again say that now this is on the telescope, and I'm showing the commissioning team there again with the fiber focal plane system now collecting spectra. I love showing this, and I don't know if this video is going to work. We were having some issues beforehand, but I hope it does. We can put some links on the website. On the left, I'm showing the theoretical trajectories of our robots, and this came out of a graduate student project from the University of Washington, Connor Sayers, working with his advisor Sarah Tuttle and his mentor Jose Sanchez Gallego, who leads our control and operation software team. They thought that this would be able to, all worked in theory, and it's wonderful to see it work in practice. And on the right, of course, showing those robots actually writhing around in our focal plane. So it actually worked, and that's just the beauty of the connection between software and hardware and theory and observation. And so Rachael showed all of this breathtaking map of the Milky Way, and I've shown this here in a slightly different scale. These are the targets that we've seen through the Apogee program. Apogee 1 begun in SDSS-3 and Apogee 2 in SDSS-4. And this is where we're headed. So these are targets in SDSS-5, filling in all of those gaps that Rachael pointed out, and all of those things we want to understand about the formation of the Milky Way and its stars and black holes. And so that I will just end and invite you to please join us, play in the data, connect with your inner scientist, and join us if you haven't already. To all the professional astronomers, we're doing it. So thank you.
Great, thank you so much. We will go ahead and move into the Q&A session. Everybody who is viewing on Zoom, note that you have a Q&A box at the bottom of your screen where you can submit questions. When you send them in, please make sure to identify yourself and your affiliation and identify who the question is for. We have at this point one question in from Bill Waller of the Galactic Inquirer. And he says to Karen and Rachel, do you foresee workshops for K through 12, K through 14? I assume that's K through 12 educators on accessing these data.
Do you want me to take that, Rachel?
I think you're more qualified.
Okay. We have done workshops using SDSS data. We have a educator focused or facing interface to the data called voyages.sdss.org, which has some lesson plans and guidance on how you can use SDSS data directly. Members of the collaboration have done workshops with local teachers. We have a program where we distribute used plug plates so teachers can own their own place of the sky. I think you email outreach@sdss.org if you're interested in that program. We have a limited capacity to send those out, but we are going to continue to do that with the remaining plug plates. We're not making any more now, so we have what we have, but we'll be distributing what we have. And then we sometimes do AAS workshops to educate other astronomers about how to use it in the classroom. So I use SDSS data in my own teaching here at Haverford, and a number of my colleagues do, and we've done workshops on that too. So I can envisage that in the future, sure.
Yeah, those plug plates were a huge hit. I remember at the AAS meeting where they were being handed out.
That's right. The AAS that happened in Seattle, which is near where they're stored. We were able to bring a larger number than is, the logistics of getting a large number was good. So
yeah.
I have a quick
Great.
question. Oh, by the way, I personally have used SDSS data in graduate classes. So Haley Wall, AAS. So Karen, you showed the hexagonal cables. Does that configuration have any advantages? I know we've seen that a couple times, especially in James Webb. Is there any technical advantage to that configuration?
I believe that for the instrument, for the building the MaNGA instrument, the choice was made because you have this lovely hexagonal close packing. So you don't have to sort the fibers pushing them in, but you can push sort of very gently, I imagine, push them in, and the piece of metal starts round and gets hexagonal. So they sort of naturally close pack. Not all IFUs have done that way. Some of them have a more random spacing, but for MaNGA, we felt that was a good choice. And then the observing was done with a dither pattern. So we try to fill in the gaps. It's all explained in the MaNGA overview paper, and on the website, you can see the impact of this dithering. So it's not just that we observe each galaxy once, we actually observe each galaxy typically 9 times through the bundle in a pattern.
Thank you.
All right, next question comes in from Rick Feinberg, the former AAS press officer. And he's asking what I was going to ask. This was great. Can you name a few of the key discoveries or advances that have emerged from the many years of SDSS to help us put all of these data and hopes and dreams for the future into context? A few highlights, and I'll even add to that, anything especially surprising. Put you all on the spot.
We were reflecting on this actually when we were practicing. Those diagrams I showed of the overview of the galaxy population showing the red sequence, the blue cloud, that was not known before, or that was not known at least to that level before SDSS happened. And it was the sort of big data revolution in extragalactic astronomy that started that view of galaxies as being red or blue and having this green valley where there's very few in between. We should probably mention cosmology. Juna, do you want
to? I would say there are so many aspects about SDSS that have been transformative, but of course the million redshifts, the really putting large scale structure in, there was hints of large scale structure and certainly maps and beautiful maps, and we can all remember Stickman, and people knew that the galaxies were clumped, but being able to detect the echoes in the baryon acoustic oscillations is just tremendous, and being able to put that into a precision science was totally transformative, as was the near field cosmology elements, which I think, Rachael, are pretty close to her heart.
Yeah, with the photometric surveys, when you were able to map 35% of the sky, they found stars and images and were able to identify stellar systems that had never been found before, because you needed that area and you needed the homogeneous photometry. So you weren't crippled by systematics field to field. So some of the most interesting satellite galaxies have been discovered, in that original Sloan imaging data. As we move into the spectroscopic surveys, one thing that there were lots of hints of things when Apogee started, just hints in different pieces of data of different aspects of the galaxy, but it was hard to disentangle because so many different projects were using different wavelength ranges, different techniques, and all of these systematics made it so hard to put together. So what Apogee wanted to do was get rid of all those systematics by looking at it all together. And so some of the things we've discovered is that there are two constituent populations in our galaxy. What's called the high alpha population, the low alpha population, but let's leave the names. But that's really important because it looks like there's something fundamentally different between those two that we're trying to understand. Something we didn't anticipate was how much pairing the spectroscopy from Apogee with the high resolution, high precision, high time resolution, high precision Kepler photometry would reveal so much about stellar astrophysics. So this field of astroseismology is just, took off when you had those spectroscopic. So astroseismology on its own, amazing. But all of a sudden you have the chemistry and you have other aspects of the stars, and we could do so much more. So we've invented tons and tons of tools and techniques along the way that now we can apply to this huge data set, like how to find ages of stars. We're working on understanding things like mixing inside of the stars. And a lot of these projects, a lot of these things that we didn't even anticipate are these foundational aspects of Milky Way Mapper. Going in, and they're going to do it on a huge scale. And these weren't even things that we thought about back then. So we're really highlighting how all of this is playing together. And then there's something wonderful about putting the data out there and seeing what everyone else does with it. Because we had ideas and we had a mission that we were going out to do, but it's nothing compared to when you have the hive mind of the entire astronomical community and all these different perspectives and angles.
And I think we kind of take that for granted now, right? Everyone makes their data open. It's all on the web. But SDSS, this is before my time, but SDSS was really the beginning of this, and the philosophy of having open data and making it available to everyone may be the most important thing that SDSS did for astronomy. Maybe.
+1. I also am a big fan of the quasars at the edge of the universe, and those are amazing. But it is, I think Karen and Rachael have really hit it on the head. If you love your data, set it free, so that more people and more science can come out, and teach people how to use it. Give them the tools. Don't just drop a bunch of bits on people, actually teach them how to use it. And in fact, because SDSS data was open, it actually made really important contributions to data science as a field. And so yeah, that open data is key.
That's great, thank you all. And Rick and I weren't the only ones with this same question. Monica Young from Sky and Telescope also said the results from these surveys are certainly word cloud worthy, and then asked what some of the most surprising findings have been. So she had written that even before I asked it too. So I'm glad you all had some great answers for that. Next question here is from Camille Carlisle of Sky and Telescope. And she asked for Juna, what are some of the specific benefits in using robots? For example, how much faster are observations?
Yeah, they're faster. And that's a great question. So it takes, in order to plug a plate and put it into the telescope, the overhead of that process is about a half an hour just to change the cartridge out. And we have an amazing group of observers and pluggers, and they've done an incredible job doing this for decades. But the number of objects that you would be getting a night goes from something like a few thousand to about 15,000. So it really is a tremendous change in terms of the speed. And we can reconfigure the actual focal plane in about 3 minutes. So think about an hour integration compared to a few minutes, or that half an hour to change your positions to now only a few minutes. So that's just an incredible speed up that we already know that there's a lot more science in this sky than than we have funding to observe. I'll say it that way. I should also add too, the individual positions. One thing we couldn't do with the plug plates is that they had to be drilled many months in advance. And so you couldn't on the fly change your target. But now when things go off in our fields, we can change a target immediately and have rapid response capability, which was not a capability that the Sloan telescope had.
Rachel, did you still want to add on there?
I was just going to comment, my subsystem I worked on in Apogee was targeting, and we planned things 9 months in advance of when we thought things would do anything on the telescope. And so you're really going from 9 months to 15 minutes, which crazy. Is, yeah, I'm sure I could do the math. It's a big improvement.
Great, thanks. Next question comes from Don Khaduk of CBC. Question for Karen. I'm curious how the images of galaxies are collected. Is there a standard exposure time, or does it vary for each target? Fascinating project, and congratulations on your successes so far.
So the original SDSS images, again, that was before my time, but that was a drift scan technique where the telescope pointed in a certain direction and waited for the sky to drift across the camera. And so the exposure time was set by the size scale of the camera. It's a pretty clever technique, actually. And so it was pretty consistent per galaxy. For MaNGA data, specifically, if you're talking about the images we take at every wavelength for these data cubes, we aim for a consistent signal to noise, but there's observational realities. So I mentioned we do this sort of 3-point dither pattern, and we aim for 3 sets of those. Ideally, gets you the right signal to noise, but sometimes you need more, and sometimes the sets don't quite match, and there are some details, basically a lot of fun details about logistics in the observing, which again had to be planned super in advance. So the MaNGA sample was very cleverly designed actually to be a representative sample of galaxies embedded in the bigger SDSS sample, but it was very fixed quite early on. So
thanks. This question comes from James Siddle, no affiliation. A general question: what are the best ways for enthusiastic amateurs to participate in research and support scientific discovery using the SDSS data? Perhaps assuming some software engineering or data analysis skills as a baseline.
Karen, this one's for you.
Yeah, all right. So, I mean, I have to mention the other project very close to my heart, the Zooniverse, and particularly Galaxy Zoo. So this is citizen science analysis of big data. We started with the SDSS images of galaxies. That's what the data set was that launched Galaxy Zoo, again, enabled by the open data of SDSS. It's always been this kind of like affiliated but separate project. Zooniverse now does all kinds of citizen science with all kinds of astronomy data. And there's projects at all different levels, from very baseline, you can just get involved in the browser, to much more in-depth projects now. So Zooniverse, we've been working a lot more about trying to get more projects that are going to make use of people's skills a bit more and allow kind of for a tailored experience. So, maybe you're a school child and you just want to classify images of galaxies, and that's great, but we have some things which are harder to do and maybe can make use of your skills. So try the Zooniverse is my advice.
Great, thanks. The next question comes from Charles Liu, who is at the City University of New York. And he asks about something that we were actually discussing just before we went live. SDSS over all its years and incarnations has become in many ways the flagship that represents the entire astronomical community to the general public. In that context, could you comment on how the collaboration has worked to promote diversity, equity, inclusion, ethics, and collegiality in the SDSS collaboration and in the field of astronomy overall?
That's you, Rachel.
Yeah, that's
Yeah.
right.
Yeah, so another hat I wear is being the co-chair of our committee on inclusiveness in SDSS, which has been a major component of Sloan 4. So we have a whole committee who just thinks about how the collaboration can be better on all angles of inclusiveness. And we take into account things like institutional affiliation. How do we bring in people who are at institutions that aren't able to buy into Sloan? We think about how we're making sure that scientists are recognized within the collaboration for their contributions. I think, there's so many axes on it. And so we have a whole committee that thinks about this all the time. And the way we spread that out is that right now we actually consult with other major collaborations. Almost all of the other major international collaborations now have a similar committee. And it's part of their mission to do research inclusion. There's other programs coming up and other ongoing big projects that are going to have huge components devoted to research inclusion, and members of our committee consult with those and review those and are out in the community doing that work. And it's amazing to recognize, Sloan has recognized technical contributions and our architects, and this came out, I think last year. Robert Lupton and David Weinberg won a huge award for their integral contributions to Sloan. And so we're seeing this change in the community to respect that technical side. And we're also seeing the respect for the members of Sloan on the inclusion side as they move out and work with other projects. And then one thing that we do with the committee, and it's critical, is we actually take data on who is in our survey and how they're participating and what their perspectives are on the survey. And they're broad. And by getting that data, we call that our annual demographic survey. And by having that data and having that information, we keep a pulse on, or we try to keep a pulse on what the collaboration feeling and is doing. And over these last couple of years, that's been extremely important because everything has just been that much more difficult. And so, part of our job on COINS is we also write papers about it, and we release that data and use that data to help others also learn about their surveys, because we're able to put some of our FTE, some of our effort into thinking about this. We're lucky that we get to do that. So we're hopefully spreading the SDSS view on inclusion, which includes things like making data public, making code public. That open data I consider part of inclusion. You're seeing that spread all across the community, and it's a real testament to the work that everyone in the collaboration does.
And I just want to add to that, a big part of SDSS involves sort of best practices and how the COINS committee really thought hard about what those are and did a lot of research on what those are to ensure that when that we're not just hiring our friends, that we're actually doing things to make sure that we're putting best practices in place so that people aren't excluded.
Thank you so much. And yeah, Charles does mention full disclosure that he is a member of the collaboration, but that was a really great question, and it's nice to hear about all the efforts that are in place and how that's kind of coordinated with other collaborations internationally. And we've got a question here from Martin Radcliffe, freelance, for Rachael. What are the top notable outcomes from understanding metallicity of stars across the plane of the Milky Way and the thicker disk? And what are the surprises there?
Yeah, so I think a really simple way to look at what Apogee's done is it's basically rewritten the textbook on how we think about the galaxy. If you go pick up a textbook, even the textbook I learned from in graduate school, and start examining some of the assumptions that are made, we found that not all of those are perfectly accurate. And this is really what comes into play with the thin disk and thick disk debate. Did the thin disk form first or the thick disk? And all of these assumptions go into how we think galaxies form and evolve. And what we're finding is that while there's a lot of complications involved into this, we're seeing things that we expected from the perspective of, we expected there to be this high alpha population, the low alpha population. But we also find things, because we can map ages onto stars now from that Kepler work, we're also finding that it's not simply old stars, young stars, which I think is something that everyone assumed. You actually have stars of similar ages on both of those tracks. And that makes you realize that, the things formed and then continue to evolve. And so you think about that component for a bit. One thing that we're also able to do is now identify, using chemical signatures, identify things all across the galaxy that look similar to each other. And that's helping us to understand how, do star clusters form and stay together? Are they being ripped apart and being distributed? How novel, how important is that to understanding the formation of our galaxy? And then a really interesting thing that Apogee has done is, by having the dynamics, we actually can separate star populations, not just on the chemical properties, but actually on their dynamic properties, and ask the question, are these really members of the disk, or are they members of a different structural component? And so basically there's very disordered motions in the halo, and there's a lot of ordered motions in these different disk components. And so a lot of times when people just assumed, if I look out of the plane, I'm getting all halo stars. Well, you're looking through the disk stars too. And so as we can actually tease these things apart very carefully and look at this nuance, we're just adding to our story and building up, which isn't a super specific answer because it gets into the weeds really fast. But the basic idea is actually putting the stars into the components that they belong, and then making those comparisons apples to apples. And we're starting to either reinvent or tweak that history of the galaxy narrative that's in the Astro 101 textbook.
Great, and we've got a question for Juna that just came in from Rick Feinberg, AAS. Is SDSS-V being done with similar equipment in both the North and South hemispheres?
Yes. So that's one of the great, so the little interesting thing is that the Sloan telescope was actually a clone of Carnegie's DuPont telescope, which is why Apogee 2 could go to the Southern hemisphere, and why we can have, now it's not a clone. When you look at them, they don't look exactly the same, but optically they're very similar, which is why you can actually very easily move the hardware from one to the other. And I say very easily with a huge asterisk, because nothing is easy, just so everyone understands that. But yeah, so this is a symmetric observing facility. We've upgraded and taken one of the BOSS spectrographs, which was the workhorse for the MaNGA survey that Karen described, and also the eBOSS survey and the BOSS survey in SDSS-3. We've taken one of those, and we will be shipping that to Las Campanas Observatory soon. The Apogee 2 spectrograph is already there waiting for us, and we have a clone focal plane system for the Southern hemisphere, although they're slightly different. They're not exactly the same, but they're close enough that we can make two at a time. And of course, just as soon as the team from OSU returned back from Apache Point, they started making everything ready for Las Campanas, and so we're hoping to send that soon. And of course, stay tuned for our local volume mapper instrument also being built at Las Campanas, which we haven't even gotten to. SDSS-V is off the chain.
Great, thanks. And we have time to squeeze in one more question from Bill Waller of Galactic Inquirer. To anyone who can answer, concerning spiral galaxy structure, is the Hubble classifying correlation between bulge prominence and spiral arm winding confirmed or nixed by your imaging survey?
Well, a question close to my heart. Yes, I I think the jury's still a little bit out on that. I have published Galaxy Zoo results suggest there was very little correlation between bulge size and arm winding, which is what Hubble found. Hubble's sample was very niche. It was very bright galaxies, very nearby galaxies. It was magnitude limited rather than volume limited. So, I mean, that was what they did at the time. It was photographic plates, right? If you make that subset of the local galaxies, you can find a correlation. But if you make a volume limited sample, you don't get such a good correlation. And I can go on for a long time actually about spiral structure. I'm very well prepared on this, but perhaps it's a little off topic. I think it's not completely confirmed that it's not right, but I think that all signs are pointing in the direction that it's more complicated than Hubble found, which is not too much of a surprise, right? We've been working on this for 100 more years. So.
Great. Thank you all so much. And I will pass it back to Macy.
All right. Thank you so much to our speakers for being here today. Thank you, Rachael, Karen, and Juna. We also want to thank the audience for showing up and asking so many great questions. We want to thank the PIOs who helped create these press releases and do the briefing prep. And we also thank our sponsor, USRA. If you're interested in viewing any bits of this press conference that you might have missed, there will be a recording on YouTube. And the press releases are now going to be on the AAS website, as well as the AAS Press Twitter account. Our next press conference is coming up in just about an hour at 2:15 Mountain Time or 4:15 Eastern. And the topic of that one is going to be stellar nurseries, clusters, and streams. And we'll see you then.